quiet in here. Subcommittee on Energy will come to order. Without objection, the chair is authorized to declare a recess of the subcommittee at any time. So welcome to today's hearing entitled Advancing Nuclear Energy, Powering the Future. I now recognize myself for 5 minutes for an opening statement. Today we're going to hear from a panel of experts on advanced nuclear energy research in the United States and discuss what we can do as a nation to advance this critical area of science. We'll also discuss the implementation of my bill, Senate S97, the Nuclear Energy Innovation Capabilities Act. Nuclear energy, as we all would agree, I believe, is a critical part of the United States energy security. Currently, the 99 nuclear power plants in the United States operating fleet generate about 20% of the total electrical output in the U.S. Nuclear also provides 60% of our emissions-free electricity. Unfortunately, our commercial nuclear fleet today is made up of entirely light water nuclear reactor designs using traditional nuclear fuels. Coupled with a long regulatory process, these reactors have become too big, too expensive, and too risky for utilities to undertake. So, that means our nuclear fleet is dwindling at the exact moment when we need it to grow. You don't need to look further than this week's news to see the hurdles facing those attempting to build new traditional nuclear plants in this country. However, advanced nuclear reactors are positioned to change the way nuclear power is sourced, produced, and managed. Decades of early-stage nuclear research conducted at the DOE national labs and renewed investment by private companies are breathing new life into this industry. As we drafted our nuclear legislation, we met with dozens of these stakeholders working to develop unique and innovative reactor designs. What we heard over and over again was that despite federal and industry investment, a significant number of research challenges remain for these reactor technologies before they are ready for the commercial license application process. We believe that my bill, S97, will help address these challenges. This bill directs DOE to partner with industry to construct and operate reactor prototypes at DOE national labs and authorizes key research infrastructure needed for next-generation nuclear R&D. We know that DOE has the expertise to lead in this arena. After all, researchers at Idaho National Lab, INL, have designed and constructed 52 pioneering nuclear reactors to date. Our national labs provide a unique environment that safely allows for testing and development of advanced nuclear technology without a burdensome regulatory process that can slow progress to an absolute crawl. While modeling and simulation can speed research, nuclear fuels and technologies must be validated through direct experimentation in the lab. That's why the cornerstone of this bill is the authorization of construction of the versatile neutron source, a research reactor capable of producing the fast neutrons needed to test so many of those advanced reactor designs. I look forward to hearing from the department and from INL, Idaho National Lab, today on what steps have been taken to accelerate construction of this critical research facility. In order to maintain our leadership in nuclear power, the U.S. must continue developing cutting-edge technology right here at home. We cannot afford to miss the economic opportunity provided by the next generation of nuclear technology, and we cannot let our best scientists and engineers go overseas. Through the implementation of S97, we will also strengthen America's ability to influence security and proliferation standards around the world as more and more developing nations look to nuclear energy to help grow their economies. I believe that with their diverse size and power capabilities, advanced nuclear reactors could also bring clean, affordable power to the most remote areas of the world. We have a responsibility to make sure that these reactors are both safe and reliable. I want to thank Ranking Member Johnson and Chairman Smith for their years of leadership in advocating for nuclear energy R&D and for helping to get our bill to the President's desk. As always, I'm very grateful for the opportunity to work alongside my Science Committee colleagues and Senate counterparts to prioritize fundamental research that will support nuclear innovation while keeping Americans safe, independent, and globally competitive. Today, we will also hear about the steps for nuclear R&D, whether it's focusing on fuels research or expanding lab capabilities. There will be more work to do to ensure we encourage innovation and make smart investments with Americans' tax dollars. I hope we can continue to work together on these issues in the years ahead. I want to thank the witnesses in advance for their testimony, and I'm looking forward to a productive discussion about how to best take advantage of this exciting and pivotal moment for advanced nuclear technology in the United States. I now recognize the ranking member.
Mr. Chairman, thank you very much for holding this hearing, and really want to thank the panelists, too. We have an esteemed group of panelists that have joined us this morning to talk about a very important subject, and that is the future of an advanced nuclear industry, an industry that may well be a player in realizing our goal of a less carbon energy future. Historically, the nuclear energy has faced a number of challenges, including high costs, long construction times, and safety concerns. However, in recent years, new design concepts and technologies have emerged with a focus on addressing these and other common concerns with nuclear energy. Advanced nuclear reactor designs have a number of benefits over the current generation of nuclear reactors. They incorporate passive safety features that prevent accidents due to human error. They have much lower waste and use nuclear fuel much more efficiently. And they can be manufactured in factories instead of on-site, reducing costs and shortening construction times. These new designs could disrupt the U.S. energy portfolio, but for that to happen, we need to make the right investments. And that's why I'm pleased that Democratic and Republican members of Congress came together earlier this month to pass the Nuclear Energy Innovation Capabilities Act. This bipartisan bill will provide the tools and resources that our scientists and engineers in government, academia, and industry need for us to be the world leader in producing the next generation of nuclear power plant. This bill authorizes a new user facility that researchers and entrepreneurs will be able to use to test and develop new fuels and materials for novel nuclear reactor designs. It also supports investments in high-performance computing to help accelerate R&D of advanced nuclear reactors without the need for costly and premature investments in physical infrastructure. And lastly, this bill authorizes a cost-share program with industry to help offset the substantial price of licensing these first-of-a-kind reactors with the Nuclear Regulatory Commission, which is currently considered to be a major barrier to ultimately deploying these advanced technologies. Beyond the implementation of this bill, I'm looking forward to the testimony of all of our witnesses here today to discuss other issues and ideas that Congress should consider as we aim to accelerate the development of the advanced nuclear industry. I'm especially interested in hearing from Dr. Parsons, who brings a unique big-picture view of the challenges that the industry is currently facing, as well as the potential for advanced nuclear energy to enable our clean energy future. And thank you, Mr. Chairman, and I want to yield back the balance of my time.
Thank you. I'm going to make the next introduction for the next opening statement. But before I do, I want to exercise personal privilege. The gentleman from Texas that I'm about to introduce is going to be leaving us at the end of this session. And I want to say that he has been a leader among leaders. He has been an absolute brilliant chairman on more than one committee. He's thoughtful, he's focused, he's been good for America. Please help me in congratulating Chairman Lamar Smith.
Thank you, Mr. Chairman. That was not expected.
Well, I haven't recognized you yet.
Well, and I appreciate your sparing those nice rumors. You set a high standard, and I'll just hope to come part way to achieving those, but many, many thanks. Also, thanks to the witnesses for taking the time to be here as well. Today, we will hear about the implementation of Science Committee Legislation S97, the Nuclear Energy Innovation Capabilities Act, which just 2 weeks ago unanimously cleared the House for the President's signature. Nuclear fission has been a proven source of safe and emission-free energy for over half a century. As this committee has repeatedly heard, advanced nuclear energy technology is the best opportunity to make reliable, safe, and emission-free power available throughout the modern and developing world. This new nuclear power technology represents one of the most promising areas for growth and innovation, increasing economic prosperity, and lowering the cost of electricity over time. Because of technical challenges and the high regulatory costs associated with licensing commercial reactors, the DOE National Laboratory System plays an important role in supporting nuclear innovation. National labs can host critical research infrastructure, while DOE researchers can investigate the fundamental scientific questions that are key to the development of next-generation nuclear fuels and reactor designs. This approach maximizes the impact of federal research dollars and facilitates the development of a wide variety of nuclear technologies. The Science Committee's legislation, S97, prioritizes infrastructure and early-stage nuclear R&D. The bill leverages DOE state-of-the-art supercomputers to accelerate the development of advanced reactors. It also creates a reliable mechanism for the private sector to partner with DOE labs. This allows industry to build prototype reactors at DOE sites and creates another pathway for American nuclear entrepreneurs to move innovative reactor technology to market. Most importantly, the bill authorizes construction of a research reactor or versatile neutron source at a DOE site. The safe development of advanced nuclear technology at DOE sites will provide access to DOE resources and expertise and fast-track the regulatory process. After 4 years of bipartisan collaboration, I'd like to thank my colleagues, particularly Energy Subcommittee Chairman Randy Weber, Ranking Member Mark Vesey, and Science Committee Ranking Member Eddie Bernice Johnson for their initiative on this subject. It is critical that we develop the next generation of nuclear reactors here at home. Our witnesses today can provide guidance on the next steps Congress should take to ensure American innovators have the tools they need to develop this groundbreaking technology. I look forward to hearing about the ways in which DOE and the national labs plan to implement this legislation and how we can continue to build on the history of American leadership in nuclear power. Thank you, Mr. Chairman. Yield back.
Thank you, Mr. Chairman. Our first witness today is Mr. Edward McGinnis, the Department of Energy's Principal Deputy Assistant Secretary for the Office of Nuclear Energy. From New Orleans. Prior to his current role, he served as the Deputy Assistant Secretary for International Nuclear Energy Policy and Cooperation, which included the role of Steering Group Chairman of the International Framework for Nuclear Energy Cooperation. Mr. McGinnis has also served as a Vice Chairman and a Principal United States Representative to the Generation 4 International Forum. Mr. McGinnis has also served as a Senior Advisor and Special Assistant to 4 Assistant Secretaries and Deputy Administrators for Non-Proliferation and National Security at the Department of Energy. He holds a master's degree from the American University School of International Service and is a graduate of the Kennedy School's Senior Executive Fellows Program, as well as the Program for Senior Executives in National and International Security at Harvard University. Welcome, Mr. McGinnis. Our next witness is Mr. Harlan Bowers. Am I saying that right? Okay, I didn't know how to say Harlan. The president of X Energy, a privately held company based in Greenbelt, Maryland. Previously, Mr. Bowers served multiple roles, including the Senior Vice President of Business Development, Vice President and Program Manager at Stinger Goffarian Technologies, or SGT. Much of his background has involved aerospace systems projects with NASA and commercial customers. Mr. Bowers received a Bachelor of Science in Aerospace and Ocean Engineering from Virginia Tech and an MBA from the University of Maryland, College Park. Welcome, Mr. Bowers. Our next witness is Dr. John Parsons, the co-chair of Massachusetts Institute of Technology, MIT, a study on the future of nuclear energy in a carbon-constrained world. Very timely. Additionally, he is the head of the MBA Finance track, co-director of MIT's Keynes Low Carbon Energy Center, and an affiliate of the MIT Center for Energy and Environmental Policy Research. Previously, he worked as vice president and principal at the economics consulting firm CRA International. Dr. Parsons holds a Bachelor of Arts in Economics from Princeton University and a PhD in Economics from Northwestern University. Welcome, Dr. Parsons. Our final witness is Dr. John, is it Wagner? This says Wagner, but you have an extra N in your name. It is Wagner. Thank you. I apologize for that. You're the Associate Laboratory Director of Idaho National Labs Nuclear Science and Technology NS&T Directorate. His previous roles included Director of Domestic Programs in NS&T and Director of the Technical Integration Office for the DOE Office of Nuclear Energy's Light Water Reactor Sustainability Program at INL. Dr. Wagner initially joined INL as the Chief Scientist at the Materials and Fuel Complex. He is a Fellow of the American Nuclear Society and recipient of the 2013 E.O. Lawrence Award. Congratulations. He has authored or co-authored more than 170 refereed. Wow, that's amazing that they referee that stuff, isn't it? Journal, and we probably could use some referees up here in Congress, I'm just saying, okay? Refereed journal and conference articles, technical reports, and conference summaries. Dr. Wagner received his Bachelor of Science in Nuclear Engineering from the Missouri University of Science and Technology and Master of Science and PhD degrees from Pennsylvania State University. Welcome, Dr. Wagner. I want to say thank you to all of y'all for being here. And we're going to start with Mr. McGinnis. And Mr. McGinnis, you have 5 minutes. You're recognized to start. Thank you.
Thank you, Mr. Chairman. Greatly appreciate the opportunity to speak before the subcommittee. Chairman Smith, Subcommittee Chairman Weber, and other members of the subcommittee, it is an absolute privilege to be here today, and we want to recognize the leadership of this subcommittee, of the committee, for your important work, including with this legislation. As the major source of reliable, clean, baseload electricity, nuclear energy is a key asset for the United States. It is, in fact, an essential element of the nation's diverse energy portfolio, helping to sustain the U.S. economy and support our national goals. A strong domestic nuclear industry enabled by the existing nuclear fleet and enhanced by innovative technology developers is critical to our national security interest as well. Today, nuclear energy is the third largest source of domestic electricity generation and is the largest source of clean energy, as you indicated, Mr. Chairman. Besides providing reliable, clean baseload electricity, nuclear power plants also provide price stability. That is an important but rarely talked about attribute of nuclear energy. Nuclear power plants serve as bedrocks to communities across the country, providing high-paying, skilled generational jobs to almost 500,000 Americans. The U.S. nuclear fleet is also a significant contributor to the federal budget and generates $10 billion in federal taxes, $2.2 billion in state taxes each year. These units are drivers of local economies as well, often serving as the largest employer and economic engine of small communities, anchors to communities, in fact. Even with all of these benefits, however, the nuclear energy sector is indeed undergoing a major transformative period of time due to a variety of factors that include changing and very challenging market conditions, an aging fleet of reactors, and an absence of nuclear energy product choices in innovative business technology deployment models available to customers. In my view, these factors are actually driving the transformative bow wave of highly innovative technologies, one of which is represented here today on this panel. Advanced additive manufacturing techniques and new innovative business models coming out of the U.S. nuclear energy sector. So what do I mean when I say the nuclear sector lacks product choice? Today, utility customers and communities around the United States who may be interested in acquiring nuclear energy's long-term, clean, and reliable source of power for their communities are faced with a rather startling, limited choice of only large or larger reactors. These large reactors can take 5 to 10 years to build before generating revenue from the power production. So additionally, many international markets find these gigawatt-class reactors as simply too large for their electricity grids. As long as there are only large and larger reactors, the nuclear energy reactor markets, in my view, will remain substantially constrained relative to nuclear energy's true market potential. So what do we do? What do we see happening to respond to this lack of product choice by those who otherwise would very much like to have the unique energy attributes offered by nuclear energy? We see the market response through the emergence of 50-plus U.S. nuclear reactor technology companies, and they are developing these highly innovative, small, scalable, flexible, versatile, and financeable reactors. These innovative concepts include small modular reactors, microreactors, high-temperature gas reactors, molten salt reactors, and even liquid metal fast reactors. We are not only seeing game-changing and highly disruptive advancements in the U.S. nuclear design space, but also in the advanced manufacturing area as well. The ultimate goal with our early-stage advanced manufacturing research and development is to enable the development of innovative processes such as 3D printing that can be applied to nuclear energy technologies. And this is what I would call game-changing. Finally, the U.S. industry is leading multiple advanced nuclear fuels development efforts with some of the design components already in the U.S. reactor fleet undergoing testing. These designs offer real potential, substantially improved economics and margins. The Advanced Fast Test Reactor is an absolute key test platform that we see will be needed to support this new class, this new bow wave of very disruptive, very promising, and very innovative technologies that are U.S. developed. So we have a unique opportunity to realize a leapfrogging effect during this inflection moment that we find ourselves in this country with regards to nuclear energy. But it is by no means too late, but it certainly is in the fourth quarter, and this is the time it will be, frankly, in my view, on my watch, on our watch, in the next 5 to 8 years, as to whether we do realize the true potential of these exciting new companies, again, like one represented here today. So thank you very much for the opportunity to testify today.
Thank you, Mr. McGinnis. Mr. Bowers, you're recognized for 5 minutes.
Thank you, Chairman Weber, Ranking Member Veazey. Thank you for your leadership and that of the members of the Energy Subcommittee on the important nuclear industry policy issues facing our country today. I have submitted a more detailed written statement and respectfully request that it be included in today's record of the hearing. And with that, I would like to summarize my testimony and respond to any questions that you may have. My name is Harlan Bowers, Harlan County, Kentucky, was where that comes from. I'm president of X Energy. Our CEO, Cam Ghaffarian, started this company 10 years ago with the altruistic desire to make a difference in the world, to find ways to deliver clean, safe, secure, and affordable energy to the U.S. electrical industry, U.S. industrial process heat users, and the needs of foreign countries. The Nuclear Energy Innovation Capabilities Act, or NECA, and the other advanced nuclear energy bills that are being considered in Congress genuinely address the obstacles that our industry face. Again, we appreciate your support and leadership. Today, our company is focused on two products, a 75 megawatt electric, high-temperature gas-cooled pebble bed reactor, we call it an HTGR, and the complementary uranium fuel. The fuel is based on the Department of Energy's investment of almost $300 million in something called tri-structural isotropic, or TRISO, particles. Over the last 9 years, we've continuously evolved our reactor concept, focusing on defining a design that employs well-understood technologies delivers electricity at rates that are competitive with fossil fuel sources, and can be readily licensed by the NRC. X-Energy is working to complete our first demonstration reactor by the mid to late 2020s. To achieve this goal, we need industry, Department of Energy, the national labs, the NRC, the investment community, and Congress to work together collectively if we're to meet the challenges in front of us. Our success at X-Energy is advanced by the programs and the entities that are supported in your legislation. Let me give you some examples. Private-public partnerships. These are needed for successful demonstration of advanced reactors. Fortunately, the Office of Nuclear Energy at the DOE, with congressional funding, has stepped up their support of advanced reactors, and we thank Deputy Assistant Secretary Ed McGinnis and his team for the work that they have done and the leadership they've provided. Through the award of competitively selected cooperative agreements, X-Energy has been able to accelerate our progress against a number of key objectives. Of course, investing in nuclear is not for the faint of heart. Several $100 million will be required to complete our design and the licensing through the NRC. That is why we're pleased to see the cost share portion and provision of the NECA legislation. These provisions are critical to the success of our industry. National labs play a vital role in supporting nuclear industry competitiveness and advanced reactor development as well. X-Energy has extensive partnerships with the Idaho National Lab and the Oak Ridge National Lab. For example, at ORNL on site, X-Energy has established a TRISO fuel fabrication facility. This collaboration represents one of the most important missions of the labs. The lab performs research to identify game-changing technologies and then partner with industry to advance that technology into the marketplace, thus making the U.S. more competitive and ensuring a technological advantage for U.S. companies. Another essential voice is the Nuclear Regulatory Commission. The NRC recognizes at the highest levels that they must modernize and improve the way that they historically carry out their regulatory mandate. Initiatives such as the Licensing Modernization Program will enable advanced reactors to be licensed more efficiently. We applaud the efforts undertaken to date and look forward to engaging with the NRC in that licensing process. In closing, let me go back to our end goal, to build and demonstrate an advanced reactor and create a new industry by the mid to late 2020s. To accomplish this, we must have high-assay, low-enriched uranium available by 2023 in order to manufacture the fuel needed to fuel those advanced reactors by 2025. This means we need to construct and license new fabrication facilities for fuel by the early 2020s. Therefore, to accomplish all this, DOE action and supportive bills such as NECA in fiscal 2019 is absolutely critical to make our collective goal a reality. X-Energy is proud to join with the outstanding leadership of this committee in executing upon the policies that will allow U.S. to reclaim our global leadership position in this great American-born nuclear industry. For energy security, for national security, and to ensure the highest standards of safety throughout the world. We at X-Energy stand ready to continue to work with this committee and with the Congress in this grand endeavor. With that, I will conclude, and I'll support any questions that you may have. Thanks very much.
Thank you, Mr. Myers. Dr. Parsons, you're recognized for 5 minutes.
Thank you, Chairman Weber, Ranking Member Veazey, and members of the committee. Thanks for inviting me here to discuss the findings of MIT's 2-year research effort conducted by a large team including other institutions such as Idaho National Laboratory. I've submitted written testimony and I'll use this time to summarize. The nuclear industry is faced with a great opportunity in the coming decades. The world needs much more energy, but at the same time, the world has to dramatically reduce its carbon emissions. Nuclear power is a proven, scalable source of low-carbon electricity, and the industry should be well-placed for growth. And yet, the grim reality is that the outlook for the industry is dim, especially here in the U.S. Our team has sought to understand the reasons for this disparity between the opportunity and the current reality. We took a fresh look at the assumption that nuclear power is needed to decarbonize the electricity sector. We examined the factors behind the alarming rise in the cost of new nuclear power plants, and we explored technologies and design options that may radically reduce that cost and the value proposition for advanced nuclear technologies. Our analysis demonstrates that nuclear power does indeed have a vital role to play in decarbonizing the electricity sector. While a variety of low-carbon technologies are now available, nuclear power can make a distinct contribution to the portfolio because it is a dispatchable low-carbon technology. In most regions of the United States, according to our analysis, including nuclear as one element of the portfolio dramatically reduces the cost of reducing carbon emissions. Nevertheless, the industry does face a fundamental problem. While other generating technologies have become cheaper in recent decades, new nuclear plants have only become costlier. Our analysis shows that the major source of costs are the large civil works surrounding the nuclear reactor and the power system. This includes the large concrete structures that are the foundation and the surrounding containment building, but also many other components of the plant. It is on these civil structures and their construction that attention must be focused. Important advances in an array of technologies that we highlight make it possible to reduce the cost of building these pieces while simultaneously improving safety. Changes to industry and practices and regulatory procedures are necessary to bring these into use, and we discuss those. These technologies are essential to any type of reactor, including advanced concepts. Without them, no concept can rely on its inherent features alone to be cost efficient. Looking to advanced reactor designs, we highlight that these provide important inherent and passive safety features, reducing the likelihood of severe accidents while also mitigating the off-site consequences of any accident that might occur. Our assessment is that the U.S. regulatory system is flexible enough to accommodate licensing of advanced reactors, but further leadership is needed to realize this possibility. We recommend ways to accelerate licensing reviews while simultaneously making them more effective in safeguarding the public. We also recommend that the U.S. establish sites where the government can assist and supervise companies as they explore new reactor concepts and demonstrate safe performance. In the U.S., sites like the Department of Energy's Idaho National Laboratory and Savannah River National Laboratory have many valuable assets and capabilities. They could be useful in designing safety protocols, seeking environmental approvals, and providing initial fuel cycle services. This committee has supported similar ideas and legislation, and we thank you for that. The U.S. should also further develop funding programs to support demonstration of these new designs, as we detail in our report. Even where all of these recommendations followed, another important ingredient is still missing. Currently, U.S. electricity markets do not compensate nuclear power plants for one of the most valuable attributes, being carbon-free. Both existing plants and investments in innovation and new builds would benefit from a level competitive playing field that fully rewards contributions to decarbonizing the electricity sector. Policies that disadvantage nuclear energy vis-a-vis other clean energy sources discourage that essential investment, raising the cost of decarbonization and slowing progress toward climate change mitigation goals. Many more findings emerge in the course of that research, and I'd be happy to discuss them with you. Thank you for your time.
Thank you, Dr. Parsons. Dr. Wagner, you're now recognized for 5 minutes.
Chairman Smith, Subcommittee Chairman Weber, Ranking Member Vesey, and members of the subcommittee. It's a pleasure and an honor to be with you.
Dr. Wagner, would you move? There you go. Thank you.
Is that better?
Yes, sir.
Sorry about that. It's a pleasure and honor to be here with you today. I'm grateful for the opportunity to testify on implementation of S97, the Nuclear Innovation Capability Act. I want to thank this committee and your colleagues in the Senate for the vision, hard work, and persistence it took to get this important legislation to where it is today. The NECA bill takes significant steps to reestablish U.S. leadership in nuclear energy and support private sector development and deployment of advanced reactors. My testimony will touch on how the Idaho National Laboratory, or INL, and other national labs will use these expanded authorities to support the private sector effort to deploy advanced reactors. First, the Versatile Reactor-Based Fast Neutron Source, or what we refer to as a Versatile Test Reactor, or VTR for short. A fast neutron test reactor is needed to support testing of advanced fuels, materials, instrumentation, and sensors. Importantly, this is a capability the U.S. does not currently possess. Development and construction of this test reactor will eliminate reliance on Russia for these irradiation tests and reposition the U.S. at the forefront of developing and improving new nuclear energy systems. The need for this capability has been well documented, and as the NECA bill moved through Congress, a multidisciplinary team of national labs, private companies, and universities have been assembled to develop the preconceptual design. The current schedule calls for the VTR to be operational by 2026. Next, I'd like to discuss the establishment of a National Reactor Innovation Center as called for in S97. In many ways, this approach harkens back to the decision in 1949 to establish the National Reactor Testing Station at what is now the Idaho National Laboratory. On this 890 square mile site in the Idaho desert, the U.S. government, including the nuclear Navy, and the private sector built, tested, and demonstrated first-of-a-kind reactors that were later deployed around the world. As Subcommittee Chairman Weber mentioned earlier, 52 different reactors were demonstrated on that site. The efforts in those days established U.S. nuclear technology leadership around the world for decades, and we're still building on that leadership today. We see the Nuclear Reactor Innovation Center as a place where government and private companies can come together to test and demonstrate new reactor designs, as well as materials, fuels, and other nuclear energy technologies. As was done in the past for light water reactors, such testing will enable advanced reactor deployment by demonstrating nuclear system operating performance and providing data and experience for licensing and data and experience for benchmarking of new computer modeling and simulation tools. Finally, NECA calls for expanded high-performance computing modeling and simulation capabilities to develop new reactor technologies. The current DOE modeling and simulation programs have made outstanding progress over the past decade for both current operating reactors and future advanced designs. In order to achieve the vision outlined in NECA, experts in modeling and simulation at the national laboratories, along with the federal staff at the DOE Office of Nuclear Energy, are formulating an ambitious plan for the future of nuclear energy modeling and simulation as a single program to start in 2020, a program I'm calling ModSim 2020. The vision for ModSim 2020 is transformation through advanced modeling and simulation of the nuclear system design and regulatory paradigm from reliance primarily on empirical data to reliance on predictive simulations supported with limited experimental data. NECA truly arrived at just the right moment. I say that because NuScale and the Utah Associated Municipal Power Systems, or UAMPS, a consortium that serves more than 40 communities in 7 western states, are looking to deploy the first small modular nuclear reactors at INL by 2026. This project has been strongly and consistently supported by Congress. Thank you. DOE and INL are engaging with the Department of Defense, as recently encouraged by the National Defense Authorization Act, to develop microreactors and allow critical national security infrastructure, such as military bases, to be self-sufficient for their power needs. These microreactors could also be used for forward-deployed U.S. military bases and remote communities in places like Alaska. DOE and INL are working with NASA to look at advanced reactors that could support the power needs for manned space missions. I appreciate the opportunity to summarize. Both the private and public sectors have a great need for advanced reactor technologies. NECA will help to meet those needs and ensure a future that is prosperous, clean, secure, and resilient. I appreciate the opportunity to testify, and I want to thank you again for your support and passage of the NECA legislation. I look forward to any questions you may have.
Thank you, Dr. Wagner. I'll now recognize myself for questions, 5 minutes. This for Dr. Wagner and Mr. McGinnis. And we'll start with you, Mr. McGinnis. We'll give Dr. Wagner a chance to wet his whistle. What is your specific role and planned approach to implementing my Bill S97, the Nuclear Energy Innovation Capabilities Act?
Thank you very much. First, let me say, obviously, we stand ready to fully implement the law once it is and at the point at which time the president signs it. But I can tell you that many of the activities that we are doing at the Department of Energy is certainly very much in line with the provisions. We greatly appreciate the leadership and support, the acknowledgement of the importance of a fast spectrum test reactor, of which we do not have in this country, and just a couple have them around the world. And it is a great disadvantage for us, and it will absolutely inhibit us from being able to support this new bow wave of highly innovative nuclear reactor designs coming into the pipeline in the United States. Certainly, also Idaho National Lab and the other national labs that we leverage effectively to support nuclear energy in the mission, they are well positioned to support the approach for a national test center for reactors, and also to work even closer with the Nuclear Regulatory Commission and the other key provisions.
Yeah, thank you for that. And Dr. Wagner, I want to come back to you. You actually said a couple things in your remarks that kind of address this. You said we want to continue to maintain leadership, and of course that would be this would be a critical area, maintaining leadership around the world. And I have to compliment, you said you're calling it ModSim 2020, which to kind of reverse engineer a phrase, instead of hindsight being 2020, this is going to be foresight is 2020. So,
I like that.
No, so I appreciate that. So what is going to be your specific role in implementing this bill?
So we have significant roles in implementing this bill, along with the federal staff in the Department of Energy, Office of Nuclear Energy. Actually, we've made tremendous progress already relative to the versatile test reactor. Let me kind of make some comments on that, if time permit. As I mentioned, the need for the versatile test reactor has been well defined. There's several different reports and industry statements about the need. So we've been moving forward even in parallel with this legislation. So with the relevant stakeholders, we've developed the functional requirements for the VTR. The mission need document, what we refer to in DOE 413 language as Critical Decision 0, is being prepared now and will be submitted in January of 2019. Last week, $3.5 million in university awards were announced to address the various technical aspects of the VTR. Earlier this month, we selected several initial university proposals to participate in the VTR program, with an emphasis on experimental designs, and we're negotiating the terms of those contracts now. In the near future, INL will award a contract to an industry partner to complete the conceptual design and cost estimate for the VTR. The current schedule calls for a completed conceptual design and cost schedule estimate as input to what they call Critical Decision 1, or CD1, to be completed in 2021. So, and as I mentioned, the plan is for the reactor to be operational in 2026. I can go on further. We have plans for the Nuclear Reactor Innovation Center, as well as ModSim 2020, if you'd like more details on those.
Well, I appreciate that, and certainly we will look to those going forward, but I'm about to run out of time. I want to get to Mr. Bowers real quick to see how your company, if you at all, do you think that the implementation of NECA will affect X Energy and its partnership with DO National Labs? I wanted you to weigh in on that, please.
Partnership with national labs, the example that I had cited in regards to development of fuel, it's important to recognize that at least 15 years, if not 20 years, of research and development was performed at both Idaho National Lab and at Oak Ridge National Lab in regards to this particular fuel form. And this fuel form is referred to as TRISO. We talked about that before, and specifically uranium oxycarbide. It's not manufactured anywhere else in the world. It is unique to the U.S., and it provides a capability within the fuel to generate more power than our competitors in China or from other countries could. So branching off from that understanding, from that capability, taking what those PhDs at Oak Ridge National Lab have learned and be able to translate that into the marketplace is key. So our goal is, as we build our commercial fabrication facility, and at the moment we are looking at Oak Ridge, Tennessee as the potential location for that facility. It's strategic to locate the fabrication facility there because we would have not instant, but very easy access to those PhDs as we're developing our commercial processes. If we have problems, issues that arise, we need some additional research to be performed to be able to go right back into the labs and use that
So
capability.
I'm over a little bit over my time, so suffice it to say, your company is well positioned to make that transition.
We are poised and ready and funded by the Department of Energy to make that happen.
Well, that's good to hear. Mr. McGinnis, I want to jump to you real quick with the committee's indulgence. You cited challenging market conditions and the availability of innovative technology as reasons as to why the nuclear energy sector is currently undergoing a transformative period. With that in mind, does it make sense for DOE to continue to provide substantial financial backing to any nuclear project that isn't A, scalable, B, cost-effective, or C, flexible? Is that going to be a hard corner to turn? What do you think?
Thank you very much. That's a very important point. First of all, I do want to qualify that there continues to be a very important role for large-scale nuclear reactors. In fact, the United States Department of Energy, thanks to the congressional leadership support, we have what is considered the most advanced, commercially available, large, passively safe set of reactors available in the world, and that is with Westinghouse's AP1000 and the ESBWR. That was hard-fought, strong technical partnership over the years with the U.S. We're proud to have supported that. Those reactors remain available. 4 have now just been completed in China, the AP1000. We're looking to the 2 in Vogtle to get done. Those provide 60 and 80
You and a
years.
whole lot of people. Keep
Yes,
going.
yes, sir. But the fact is they do play very important roles. However, as I indicated, I believe that there is a far greater percentage of market out there, customers that want nuclear, clean, baseload nuclear, but these products, large and large, are just too large. They need product choice. They need to be able to go in and not bet the farm with the company's balance sheet. And so that's why we think that this is going to open up an entirely new market and give customers finally the option to access nuclear without the choice of betting the farm and waiting 5-10 years to see any revenue generation.
Yeah, well, thank you for that. That was our hope. Thank you. And I apologize to the committee for being over time. Mr. Tonko, you are recognized for 5 minutes.
Thank you, Mr. Chair, and thank you to all of our witnesses for joining us on what is a very important discussion. Dr. Parsons, thank you for sharing some details of MIT's Future of Nuclear Power study. There are many members that want to see us make significant reductions in carbon pollution, and it behooves us to better understand the role that preserving existing nuclear capacity and developing new advanced nuclear resources might play in achieving that ultimate goal of deep decarbonization. From the modeling done in your study, what did you find in terms of reaching that 90 to 100% greenhouse gas reduction?
Thank you. First of all, the existing nuclear reactors are absolutely essential for reaching even a modest reduction. They provide the lion's share right now of low-carbon electricity, and the cost of providing that is the cheapest of the ways to provide low-carbon electricity. So it's very concerning that some of those plants have recently been closed and that a number of them are economically threatened. A commitment to decarbonization really will require a commitment to keeping those reactors operating.
And if nuclear is not part of the generation mix at those levels, what is the impact on electricity affordability?
Well, the major advantage of putting nuclear into the mix is to keep the cost of decarbonization from escalating. Nuclear keeps the cost lower and makes the electricity much more affordable and the decarbonization task much more affordable.
And what do you attribute to these costs? Is it primarily from the current cost of energy storage?
Right. Well, some of the most valuable low-carbon electricity sources, such as wind and solar, are reliant on the resource of the wind or the sun, and they're only available in certain hours of the day and at variable amounts during seasons of the year. In order to provide carbon-free electricity at all hours of the year, you would need a build-out of that capacity that's at a very, very high scale. So an initial build-out provides you what you need, but in order to cover all of the hours, the build-out starts escalating and the costs start escalating.
If we continue to invest in R&D dollars for energy innovation, including both advanced nuclear technologies and storage, can we expect to reduce those costs?
Yes, nobody knows what the future holds. Each of these different technologies may be able to provide a critical contribution in the future. Batteries can be terribly valuable. Advanced nuclear can be terribly valuable. And we need to have, so to speak, many shots on goal in order to keep the opportunities available to society.
And while many consider nuclear to be important in the overall efforts for a decarbonized energy future, I think there is equal concern by the reported cost overruns at the Vogtle plant. Dr. Parsons, can you help us understand where these unexpected costs are coming from?
Yes, you're certainly right that those costs are very critical and need to be brought under control. We did a significant amount of research on this, and we identified that most of the costs, the large lion's share of the costs, and certainly of the cost overruns, are in the construction of the civil structures surrounding the nuclear reactor and the power system. And so that construction process needs to be dramatically rationalized, and new technologies need to be applied to reduce the costs of those structures.
And what recommendations would you offer to make certain that advanced reactors might be able to be constructed without those same concerns for cost overruns with the civil infrastructure?
Well, it's important to realize that these kinds of civil structures are essential to any kind of nuclear reactor. So whatever design one's developing, we need to make an investment in the construction technologies that will make those all designs affordable. The kinds of research and development funding that this committee has supported, that DOE has done in the past, have created opportunities which we could utilize now to reduce those costs.
And we don't always connect the dots between some of these breakthroughs in the foundation construction and the industries that might benefit from them, but it highlights the importance, I believe, of cross-cutting research. Are there concerns that cuts in federal research may limit the potential of nuclear energy to reduce costs and improve safety?
Right. To meet the future, we need future technologies. And so the research and development funds that have been granted in the past have given us opportunities, but we're going to need many more to meet this challenge.
Well, I appreciate your testimony and the role that nuclear can play in a decarbonization agenda, and thank you for the thoughtfulness behind the study.
Thanks for
With
the
that, Mr. Chair, I yield back.
Thank you, Ms. Tonko. The chair now recognizes Mr. Brooks of Alabama.
Thank you, Mr. Chairman. Deputy Secretary McGinnis, I don't know if you're in a position where you can spread the word within the Department of Energy, but we need some help. In the Tennessee Valley, there is a nuclear power plant called Bellefonte. TVA has spent over $6 billion on this facility. They recently sold it at public auction for $111 million, which may very well make it the biggest boondoggle in the history of the federal government, particularly with respect to non-defense. Perhaps there are some defense things that are competitive. And for that $6+ billion spent, we've had this much electricity generated, zero. There is an effort now to get that facility completed by the private sector. There are things that have to be done through the Department of Energy. If there's anything you can do, sending the message back, know that the people of Jackson County, Alabama would very much appreciate it, because the University of Alabama has projected that this facility is completed would generate over 1,000 jobs with an average salary of $136,000 per job. That's pretty doggone good in the state of Alabama. So with that as a backdrop, let me talk a little bit more to the point of this hearing today. In 2017, there were 99 nuclear power plants in 30 states in the United States operating fleet, which generated approximately 805 billion kilowatt hours of energy. This is equivalent to 20% of total United States electrical output and 60% of its emissions-free electricity. There's been some comment to that already. I wanted to reemphasize it. One fingertip-sized uranium fuel pellet about this big can generate as much energy as 17,000 cubic feet of natural gas or 149 gallons of oil or 1 ton of carbon, to kind of put it into perspective. We've got some political interest groups that would just assume that we not have any nuclear energy in the United States or on planet Earth for that matter. Very quickly, can you describe what the impact on America would be if we were to suddenly decide that we're no longer going to have nuclear energy over the next year or two? What would be the impact on the power grid and the ability of America to continue to function as we are today?
The impact would be incredibly negative, substantive, and long-term, not only from a resiliency perspective, needing to have 24/7, 365 days a year has or electricity available, not just when the sun is shining and when the wind is blowing. I would submit that nuclear energy has an absolute necessary role in all of the above. And don't get me wrong, we need all of the above. But nuclear energy still remains utterly unique. As you indicated, sir, density of power, there is no other power source that provides the density of power. There's another interesting fact. We have about 7,700 of all shapes and sizes electricity generating plants around the country, wind, solar, natural gas, coal, you name it, 7,700. Now it's 59 of those sites is nuclear. So less than 1% of all the generating plants in this country is generating 60% of our clean, 20% of our electricity. The density of power is unmatched. And the longevity, there is no other source that can go all out, full power, 24/7 for 18 to 24 months. So
let me try to interject just for a moment, since I only got a minute left, and focus on things that I think the general public can better understand. What would be the impact on brownouts, blackouts where you have no electricity, or electricity rates if we were to eliminate the nuclear power production over the next year or two, like a lot of these political activists over on the left want to do?
I can tell you that's exactly what we're looking at the Department of Energy, especially with the grid modernization initiative. We are very concerned if we were to exit nuclear, the impacts to the stability of the grid, the availability, like Secretary Perry said, whether it's in the wintertime or in the summer, we want our family to be able to know that that power is available. And it's not just from natural made, man-made threats. We have an evolving grid that is increasingly reliant on intermittence that's driven by when the sun is out and when this wind is blowing. And that is going to truly challenge our ability to deal with not when everything's going well, but when things go wrong. And there will be times, whether it's man-made or natural, and we need to make sure our grid is resilient, and nuclear is an absolute fundamental element of that.
Thank you, Mr. McGinnis. Mr. Chairman, I yield back.
All right, thank you, sir. And Mr. Vesey, you are now recognized for 5 minutes.
Thank you, Mr. Chair. I understand that MIT published its first report on the future of nuclear power back in 2003. And I wanted to ask Dr. Parsons, what are the most significant differences about the future of nuclear energy between the publication of that first report 15 years ago and now?
Yes, well, the situation has dramatically changed. On the one hand, we have some cheaper competing sources of energy. So America's cheap natural gas provides a cheap source of energy, unfortunately with carbon, but nevertheless beneficial for customers. And then renewables have become much cheaper, providing another great option for reducing carbon emissions and providing low-cost power. Of course, the Fukushima nuclear disaster happened in between, and that has obviously raised public concerns, and that's a major important thing that needs to be addressed by the industry. And dramatically, nuclear has not achieved the lower cost targets that were advertised at the time and people hoped would be achieved. So nuclear faces significant challenges to be an important player in achieving our goals going forward. And that's why we did the study, to address those challenges.
Excuse me. How would you compare the merits of a technology-neutral price on carbon emissions to the merits of recent proposals by the administration to subsidize nuclear and coal plants? As you know, that was a very controversial proposal that came out, and largely based on the arguments of their contribution to the reliability and resilience of our electric grid.
Well, the cases vary one by one, and the situations vary in different regions. But we investigated this problem, and as I've indicated, if we let these nuclear power plants retire, that's going to lose one of our lowest cost sources of low carbon electricity. The value of these nuclear power plants is in the low carbon characteristics. We haven't been able to find any unique or substantive other values above and beyond that that would provide an economic rationale for keeping most of these reactors open. But the cost, the value of the low carbon electricity is more than enough to make these units competitive.
In your testimony, you note that the growth of nuclear industry has been hindered by public concerns about the consequences of severe accidents in traditional Gen 2 nuclear power plant designs. Can you talk about some of the advancements made by Gen 4 reactors that you think would maybe help quell some of the concerns that the public has?
Sure. Well, first of all, I think by and large we believe that nuclear power is generally a safe form of producing energy, and the problems that we really face are with some of the emissions from other forms of energy that nuclear doesn't provide. But obviously, catastrophic accidents sear the mind of anybody who sees them. I personally remember waking up early in the morning in 2011, March 2011, and seeing the tsunamis in live action in Japan, and it was just very impressive. And then in the days after, watching the news in live action, seeing some of the explosions happen at that nuclear reactor. So I'm personally very clear on how that can impact you and make you appreciate the dangers facing things. Many of these new reactor designs have the characteristic that not only do events like that happen less often, but they control the operation of the plant in the event of an accident so that you don't have any likelihood of major explosions or disruptions of that sort. And if you went to such an event, they contain the dangers within the plant boundary. And so that's the hope of developing these reactor designs, that they would make it for the public something that would be perhaps more of a normal industrial accident. Tragic whenever it happens, but something more comprehensible and less difficult to understand.
Yeah, thank you. Mr. Chairman, I yield back.
Thank you, sir. Mr. Hultgren, you're recognized for 5 minutes.
Thank you, Chairman Weber. Thank you, each one of you. Appreciate your work, appreciate your time being here today. I'm going to address my first couple of questions to Mr. McGinnis, if I might. What's the mission of DOE's Gateway for Accelerated Innovation in Nuclear or GAIN program? And wonder if you could share some examples of industry partners who are licensing and commercialization processors were accelerated by this program.
Thank you very much. The purpose of GAIN is to essentially support a very streamlined, efficient access to our nation's, the Department of Energy's world-class nuclear-related facilities, whether it's Idaho National Lab or among the other 17 total labs in the complex. And we've listened in as carefully as possible from industry with feedback. And one thing we've heard was they need unfettered, efficient access to these facilities to be able to prove out, test out their innovative concepts. And many of these capabilities we have great investments from the taxpayer, and they are world-class. So it is very important to do that. We have a multitude of companies that we provide support through GAIN, and so we're very proud of that, literally in the dozens. Leading vendors, utilities, technology developers, fuel developers. It's a very successful program, and we look forward to continuing to support that program.
That's great, thanks. Also, Mr. McGinnis, we understand that there are some delays in DOE's site permitting process for privately funded reactors. What's the status of DOE's site use permit process for privately funded reactors, and what are some of the reasons for the delays?
I'm not sure of the specific references you're making, but I can say from the Idaho National Lab, for which my office is responsible for stewardship-wise, we're very proud that Idaho has served essentially for the venue for 52 different first-of-a-kind reactors built in its history, and we have at least 3 agreements, site use agreements right now with U.S. And other innovators. One is a microreactor, one is NuScale, which I think is really in the forefront and it's in its position to potentially be our nation's first advanced small modular reactor. We are working as hard as possible to make sure that these agreements are being let out in an efficient way. From a nuclear energy perspective, it's my understanding, and I've been watching them very closely, they are proceeding. We have those in place now. When we get applications through our Idaho Operations Office, we prioritize that. We get it. We are in an extremely challenging time, and time is not our friend. So we are going to continue to get the feedback to make it as efficient as possible and improve that process to make it as user-friendly as possible.
Good, thank you. Mr. Bowers, in X-Energy's partnership with the Department of Energy National Laboratories, how is the intellectual property associated with your nuclear designs and concepts managed? And is there anything about this process that you believe could be improved?
Intellectual property is truly, as you have identified, a key aspect of what we're trying to accomplish. I can also take that from the perspective of we want to ensure that it remains a U.S. Capability and protect that from an IT security perspective. The work that we are performing at Oak Ridge National Lab today, as I alluded to earlier, it really enables us to take our reactor and make it a thoroughbred in comparison to some of our competitors internationally. So it is very important for us to retain that and protect that. As a small business, the DOE does allow us to apply for a patent waiver, and so we are able to claim patents associated with the work that we are performing both at the national labs and under contract with the DOE, and therefore we have ownership of that and can proceed forward with that. So I would say to date that the partnership has been good, and we continue to find new, innovative, and novel things that will make our designs better, and we have been able to retain the ownership of that knowledge as we move forward.
Great. Quickly, Dr. Wagner, just a quick question for you. What is INL doing to support the management and archiving of legacy reactor test data?
Actually, that's a great question because there is a great deal of that legacy data out there, and it's in high demand from the reactor developers currently. And so actually we have a number of programs with other laboratories, including Argonne National Laboratory, to basically assemble, process, and make data available from past reactor experiments like TREAT and LOFT and EBR2. Honestly, we need to do more. But we are working on that.
Good. Again, thank you all. Chairman, thank you for hosting this committee, and I yield back.
Thank you, sir. The gentlelady from Nevada is recognized for 5 minutes.
Thank you, Mr. Chairman, and our distinguished panel for joining us here today. As we discuss the future of nuclear energy and developing technologies, the one question I really think we have to answer is this: where will we store or dispose of the waste? Now, I'm from Nevada. As my colleagues on this committee have heard me say before, I strongly oppose our country storing nuclear waste at Yucca Mountain for many reasons. The site continues to present serious safety and environmental concerns, which are detailed in hundreds of contentions filed by our state. These alone will take years to address, but even if the site was green-lighted, it would take up to 50 years to build the infrastructure in Nevada and across the country and allow the waste to be cooled and shipped by road and rail through heavily populated communities like all of us represent. So I have a two-part question for anybody who like to jump in first. So to what extent are researchers and industry proposing solutions to the nuclear waste, the long-term storage problem that may not involve Yucca Mountain? And then what technologies are on the horizon that you believe could significantly reduce or even eliminate the need for large-scale, long-term geologic repository for nuclear waste? For example, reducing waste in place.
Thank you. I'd like to start by talking about fuel cycle in that regard. We are moving forward right now with uranium-based fuel. I mentioned uranium oxycarbide, which does have, we do have spent fuel at the end of our reactors, the 60-year life. And there is a storage requirement, and there are, certainly measured in thousands of years of radioactivity of that material. The high-temperature gas-cooled reactor does offer the opportunity to do a different fuel cycle, which is thorium-based. There is more thorium in the Earth than there is uranium. The way that the fuel would perform within the reactor is absolutely identical to how it would be worked using the uranium approach. And the half-life is measured on the order of a couple hundred years. So while there still is a storage requirement, the concern of millennium-long storage, long-term storage facilities becomes mitigated as we move forward and we can advance the technology for thorium-based fuel. Thank you.
Anyone else want to comment? Thank you.
So first of all, I think any of the reactor technologies that we'd be discussing will all require some sort of short-term storage and some sort of long-term repository of one sort or another. So it's an inescapable choice that we have to make. Secondly, we did not provide any new results scientifically about waste in our report, but we did highlight that there have been several studies done previously. We had done a study back in 2011. There's been a Blue Ribbon Commission. There are others that have provided sensible solutions and options for the United States. In particular, we highlight that it's very important to get consensus and consensus-based siting, precisely because we do need to move forward. And there has been a demonstration of successful consensus-based siting in both Finland and Sweden, and it could be a very valuable thing. Investors in new technologies are very concerned if a piece of the arrangement has not been settled. And so settling a piece of the arrangement would help facilitate investments.
You just answered my next question on consent-based siting. So I'm going to move on to another question. Something that we talk about a lot in this committee is early-stage research and late-stage research. It's used in a very cavalier fashion sometimes in this 2019 budget as a rationale to cut one program, maybe fund another. We haven't really defined those terms, I don't think, adequately. So is it your belief, Mr. McGinnis, I'll ask you this, that policymakers can and should draw a bright red line between basic and applied research, or between early stage and late stage research? Or should we be realistic and identify where the government can play that valuable role in de-risking technologies to partner with industry?
Thank you very much. Those are very important points. I'm in an office that is an applied energy office, and I have the great fortune to be working with innovative, first-of-a-kind designers such as here today. And the first-of-a-kind designs, I think, are dramatically different from a known technology that's in the market. With regards to early-stage R&D, then, therefore, I would say that the idea of where early-stage R&D starts and stops, it's much greater down the pathway of deployment of a first-of-a-kind technology because it is so intensively technically driven, modeling and simulation, the materials going through the entire stage of the NRC process. For example, of a first-of-a-kind, one might find themselves having to go back to what is called Tier 2 or 3 issues, where they have to go back to the basic science. So you have a flow of early stage in a broader breadth for first-of-a-kind, if that makes sense. But it is a very important point. I would say ultimately the sweet spot for the federal government in partnering with companies is when they have very challenging technical issues that they have not been able to dispatch, and that we, the federal government, are uniquely in position using our advanced test reactors or other sites to bring them to bear. So that's where we're proud to do that, and in my view, it is consistent with early stage R&D as a focus with what we're doing here today with our technical partners.
Thank you very much.
Thank you, ma'am. And now the chair recognizes one of the newer members, the gentleman from Texas. Is it Victoria?
Victoria.
Victoria, you're recognized for 5 minutes, Mr. Cloud.
Thank you, Chairman. Thank you for being here. Thank you for hosting this committee on advancing nuclear technology. This is an important topic, of course, for me because we have a nuclear plant in our district in Matagorda County. So it's important, of course, to the nation. Mr. McGinnis, you mentioned in your testimony that nuclear power plants service bedrocks to communities across the country, providing high-paid, skilled jobs to almost 500,000 Americans. Of course, this is true in Matagorda County in our district. What I hear from the folks at the nuclear power plant in our district is that regulatory oversight by the Nuclear Regulatory Commission is heavy with low-value inspections and regulations that do little for the safety of public but drive up the costs in an industry that's among the safest in the country. In 2016, the Nuclear Energy Institute testified that since 2011, the NRC has on average nearly doubled the time it takes to review license renewal and power uprate applications. A study by the American Action Forum discovered that the average nuclear power plant must comply with regulatory burden of at least $8.6 million annually, and a regulatory cost imposed on nuclear power plants by the NRC since 2006 have totaled $440 million. So, Mr. McGinnis, could you share with the committee the administration's view on the current regulatory environment?
Thank you very much, and I do want to also give a huge shout out for Matagorda County with South Texas Nuclear Power Plant. It is just an absolute example of resilient power, having gone through extreme weather events and been there with some amazing stories of the commitment of the employees at that nuclear power plant and the leadership of the county. So I want to thank Matagorda County for the leadership for really the country. We appreciate that. With regards to the regulatory environment, I think, first of all, first principles is I believe that one can have an absolute top level of safety while seeking maximum efficiency, cost effectiveness, and speed. I believe it is possible to continue to realize greater efficiency in the regulatory process. I believe that the leadership that is now at the Nuclear Regulatory Commission understands that. We see a lot of, we see examples of them working hard to be as efficient as possible because time is money for these companies, and it is incredibly challenging to get these technologies, especially new innovative technologies, through a regulatory environment. And we want to do everything we can to support and not discourage these great innovators to come in and change the future of our nuclear energy landscape. A couple of examples, we're working with the Nuclear Regulatory Commission to bring to bear our modeling and simulation capabilities. We have now the fastest supercomputer in the world now, and that's Summit and in Oak Ridge. We have tremendous capabilities NRC uses our assets. We're proud that we developed a draft set of guidelines for advanced reactors, submitted them, and they were largely accepted. We continue to partner with them, but I think everybody would agree, they included, that we want to continue to try and reduce the time and cost for these applications.
Thank you. Would you say that the current regulatory environment then matches, or what would be your opinion on the regulatory environment versus the successful track record of existing nuclear plants?
Well, I think that for many understandable reasons, the regulatory environment is set up for the current reactors, large light water reactors. That's what we've had for decades and decades. So what we're attempting to do is support in any way we can, recognizing the important independence of the NRC, to be ready with the expertise and the regulatory processes for these new disruptive technologies, some of which have completely different, very different attributes, some mentioned here today. Passive safe systems that are designed to literally shut down on their own without any human intervention, any pumps or electric-driven pumps or motors in the event of a loss of offsite power or coolant. That is revolutionary. Not only is it huge for public confidence to be able to look a citizen in the eye and say, the next generation, while the reactors are safe here today, the next ones are game changers. These are reactors that will shut down on their own, and then you have market opportunity and distributed opportunity. We see the NRC, they just exempted the electric pumps and motor requirement for NuScale, the first reactor going through this process. And the second thing they're looking at now is whether now do you need a 10-mile emergency planning zone? And if you don't, we have a distributed opportunity with safety built in that we never had, market opportunity. So I think there is a strong, significant progress being made, but certainly they are working hard at the NRC to get ready for an entirely new class of reactors. That's the challenge.
Thank you.
You may not know, Mr. Cloud, but when I was a state rep, those were the days before I got demoted, I had STP in my district. I had Matagorda County. In 2010, we went there, my staff and I, and watched them change out their fuel rods. That was pretty cool. And by the way, they have a 7,000, if I remember right, 7,000 acre water pond, cooling water pond, and got great alligator hunting. I'm just saying. The gentleman from California is now recognized for 5 minutes.
Well, I thank Chairman Weber for your personal anecdotes there. They're always useful and interesting. And I think the panel there for this morning for coming in to testify. I was going to, Mr. McGinnis, I was going to ask the fail-safe question because I've always been nervous after the Fukushima disaster, but it sounds like you're on that one. I mean, if it fails safe and it fails badly, then something's wrong with the system. So you're giving us assurance that these new designs are real fail-safe, that they're passive, that they can shut down without human intervention, and if there's a disaster like a flood, they still won't cause problems.
Thank you very much. And I think the best person to answer that is a person leading one of those designs here today.
I was really hoping you would hand that one off to me.
Okay.
If you'll allow me.
Yes.
So the pebble bed, or just in general, the high-temperature gas-cooled reactors do have this capability to self-moderate themselves. So as the temperature rises and gets, quote-unquote, too hot, the reactivity stops. And so then as reactivity slows down, the temperature drops again, and then this cycle continues to take place over several hours to several days. So then the question is, really, has this ever been demonstrated? So for high-temperature gas-cooled reactors, there have been a half a dozen built around the world over the last 40 years. And there have been 3 tests that were performed, one in Germany, one in Japan, and one in China, where the coolant, which was helium in those cases, was evacuated from the reactor, and then they watched the temperatures and the reactivity within the reactor to see what happens. And as predicted by the physicists, the temperatures rose, and then self-moderation took over, the temperatures dropped back down again, and the reactivity subsided. So it's been test-demonstrated passive safety, that there was no need for any active systems to ensure that the reactivity was maintained under control.
So now that you brought up the physicist,
I'm an engineer,
okay,
by the way.
I'm a mathematician, so we both have a thing with physics. But how about using artificial intelligence in designing reactors, like the small modular reactors? Are we going to be able to use big data and artificial intelligence to come up with really highly effective designs? Whoever, Dr. Parsons, would that be your bailiwick? No?
I will venture out a little bit on that one and maybe hit it on the side, which is to note that for the previous decades, we have various modeling and simulation codes that have been developed. And the question is always, how do you ensure that your code is accurate, that the numbers that you get out of it are correct? And that's always been performed via test. So you would set up a large-scale test of some kind, run that test, get results, test results, measurements, temperatures, et cetera, and you would compare that to the results that you're getting from your software codes. The capabilities of software, the capabilities of computing power, such as the cluster that's available at Oak Ridge National Lab, really offers us an opportunity to reduce the cost of development and use modeling and simulation almost exclusively, rather than relying on these very large, complex test systems for verification. So I think there's a lot of opportunity in advanced modeling and simulation going forward.
Thank you. I'm sorry I came in late. I was going to ask Dr. Parsons about his MIT report in using nuclear power to balance renewable energy and the cost that renewable energy might have without nuclear power. Could you expand on that a little bit, Dr. Parsons?
Sure. Well, I'll just say quickly that it's great that we've seen enormous cost reductions in renewable energy, and they've provided us a great opportunity to make some good steps forward in reducing carbon emissions. The problem is that the farther and farther you go in making reductions in carbon emissions, you start needing eventually to multiply your investments in the renewables. So the cost isn't linear. It becomes nonlinear as you go to really deep carbon reductions. And that's the role that we point out nuclear can play, to cap that escalation of costs by providing the balance of power when renewables have a modest amount of resource available. And keeping that cap on, I think, would be important for accomplishing our goals.
Is nuclear technology ready for that?
Certainly nuclear technology is ready for that, but we do need to make it, if we can make some of the cost reduction targets we describe, it makes a big impact on how low that cap can be.
Thank you, Mr. Chairman. Are you going to do another round of questions, or is this it?
Well, do I get to do my anecdotes?
Please, don't.
The gentleman's time has expired. The chair now recognizes the gentleman from California.
All right, Mr. Chairman, were those alligators, did they glow in the dark? Is this?
I've not gotten close enough to find out.
All right. Let me just say thank you. I'm sorry I was late. When you're here, you got 3 or 4 different things to do, and I've really appreciated the testimony I've heard so far, and I will be reading your submitted testimony in the meantime. Are any of you advocating building new light water reactors? Okay.
Absolutely.
Okay. We have a light water reactor in my area, San Onofre, and they are now storing the rods that are left over, this nuclear waste, at a cost of $70 million a year, and no electricity is being produced for hundreds of years. Are you sure that it's worthwhile building light water reactors?
Thank you very much. First, I want to say that the new class of advanced reactors coming down the pike include both light water and non-light water. These designs, the non-light water, are frankly, I think, in my view, very exciting. They include these passive safe, some would call walkaway safe designs.
Right.
And certainly, ultimately, beyond that, the class of reactors, non-light water, they're in a position to consume and reduce the amount of waste ultimately. But we certainly support also the full life of these reactors. I just got back from Pennsylvania at the State House, where they have 3 reactors in Pennsylvania that is slated to shut down early. If they shut down early, they would wipe out all of the wind and solar contribution in the PJM market in all 13 states where PJM is in one fell swoop, because you will lose that much emissions-free generation.
Right.
And how much of a danger do you think would be put upon the people of the area if they had a Fukushima-type incident because I imagine the Fukushima alternative was sold to the Japanese. If this can never, nothing can ever go wrong, and then we end up with a catastrophe in Japan. And that's, again, we've sold them on the light water reactor.
I have great faith in the NRC. They have realized a lot of lessons learned from Fukushima and put them into the light water reactor plants that are being operated today. But ultimately, I also believe it is absolutely necessary. We need to find a pathway to take the spent fuel that is on these sites and put them in a disposal in a repository and stop kicking the can.
Yeah, is it possible that the leftover waste, it's already been mentioned by Dr. Bowers that some of that waste is actually going to be used as fuel for the next generation of nuclear power that would not be light water?
I will comment that there are advanced reactor concepts and designs that have been put forward that do take reprocessed fuel or spent fuel and can use that as fuel for their reactors. I will comment that that is not the design that we are moving forward with, but I know that Ed is very familiar with
I think
some
that
of
we
those
should,
concepts.
when you consider that we're saying that in my area, in the middle of a residential area, that we're going to be storing nuclear power rods for 1,000 years is unacceptable to anybody. And who knows what type of dangers will come up. Who knows if we'll have a California earthquake that they were putting hundreds of thousands of people's lives, maybe millions of people's lives at stake with that type of reasoning. And I would hope that we would proceed, and say, light water reactors had their day. What can we do now to improve nuclear energy and its ability to provide for the needs of the people of the country? Mr. Bowers, your mention on the high-temperature gas-cooled reactors, I think that there are a number of those alternatives that seem to be, to me, make more sense, that you're going to have far less waste and waste that perhaps they can be used. We can use up the waste from the reactors before. Let me ask you this. Is any of this based on fusion energy? No, okay. Well, how much money are we spending on fusion energy? We've spent billions of dollars developing fusion energy. Again, I believe that's a total waste. And the fact is, we should use that money that we're spending on developing fusion, and let's spend it on some of the ideas that you have for the next generation of fission that we know we are capable of achieving. They say fusion energy is the fuel of the future, and it always will be. Well, the fact is, we need something that we're going to invest in that actually is foreseeable that we're going to be able to achieve, and not a dream. And so, number one, I will read your report. I'm anxious. I think nuclear energy has a vital role to play. We are going to eventually run out, humankind will run out of fossil fuel eventually. It may not make sense right now, but even the things we're talking about are 10 to 20 years down the road. And if we're doing that, what's the price of gas and oil going to be like then? Well, I think it will be, it will totally justify the expenditure of
developing a new generation of nuclear power. We need a new generation. We need to deal with the waste from the last generation, and we should not, again, Mr. Chairman, one of the things I'm really worried about is that we do have a profit-making as part of the equation as to what direction we go. But the people who are thinking about profit-making are not thinking at all about long-term effects on safety 100 years from now. They could care less about that. So it's up to our scientists, our engineers, and yes, elected representatives to take these things into consideration. We appreciate the guidance you've given us.
Well, we've had a request for round two from my good friend from California. And since apparently I need to recompense with him over my comments, we're going to do that. And it helps me too, Jerry. I've got some questions too, so with your indulgence. This is for Dr. Wagner, Mr. Barris, and Mr. McGinnis. In y'all's prepared testimonies, y'all emphasize the need for DOE to support research that will make high-assay, low-enriched uranium. Are you calling that HALEU? What do you?
HALEU or
HALEU, okay.
high-assay LEU.
Okay,
Terms
perfect.
of art.
Fuel available for advanced reactor technologies. So what is HALEU fuel, and why is it needed to advance the next generation of reactor technologies? And Mr. Bowers, we'll start with you.
Thank you very much. So we start with the definition, right? All existing light water reactors operate on fuel enriched uranium that is at a enrichment of less than 5%, 4.8, 5.1, and down from there. The military needs for uranium start at, as well as some test reactors within the United States, start at 20% and go up. So there's this no man's land, this range between 5% and 20% enrichment that's called high-assay, low-enriched uranium. Several of the advanced reactors are looking to use high-assay LEU for their reactors. That enables higher burnups, improved efficiencies, longer periods of time between outages. So there are a lot of benefits to using it.
So why hasn't that been done heretofore?
The demand for uranium, demand for product, has been driven by what the market currently requires, which is light water reactors at 5%. So no one's going to build a factory to make something that makes 8% if no one's going to buy it. And the needs for the test reactors is relatively small, and so that's been able to be supported by DOE, Y-12, and other sources within the U.S. I'll stop there.
Mr. McGinnis?
Well, I don't want to add more to his technically sound description, so let me just describe briefly the demand. We actually have, there is no high-assay LEU commercially available on the planet right now. The majority of the new innovative
Not even for testing?
There was
Oh, you're saying commercially available?
commercially available. Okay. So no U.S. company that is looking to bring in their reactor right now, they have no high-assay LEU fuel. They have no fuel for their design. And that creates a great risk. The closer they get to trying to deploy, they can't sustain that risk, not knowing there is none. That doesn't mean that enrichment facilities can't move forward when they see enough of a market, a customer demand, but we have a chicken and the egg here.
Is that a short startup time?
Not that short. Be able to get this established with the high-assay LEU, you're talking a couple of years at least. So it's not going to be immediate. However, that's where I think the Department of Energy is in a unique position to help spur and support at least the laboratory scale, if not a little bit larger scale, for the demonstration of high-assay LEU for these new reactors to provide the confidence. We have micro reactors. Many people may not realize this. They may be coming in as early as 2021, 2022. These are reactors that will need high-assay LEU.
Are you calling SMRs micro-reactors?
Micro-reactors are smaller than SMRs, so micro-reactors, depending on the definition, and in general, it's 1 to 5 megawatts electric. Some define it up to 50 megawatt, but in truth, most of the micro reactors are about 1 to 5 megawatt electric. But 1 megawatt electric, that supplies power to 1,000 homes. So that's not insignificant. So we have a very near-term need for the ability to provide confidence to these new innovators in the markets that highest HALEU will be available when needed.
Okay, thank you. Dr. Wagner?
I would just add that some of the accident-tolerant fuel concepts for the existing light water reactor fleet are also looking at enrichment above 5%, more in the lower range, 5 to 8%. So some of those concepts also have a need here for this fuel as well, whereas the advanced reactors are primarily looking at right close to 20 weight percent. With the support from the department, we're actually taking several steps, but we need to do more. Some of that is initially recovering high-enriched uranium from spent fuel, such as our EBR2 fuel.
And that's what France does?
No, France reprocesses commercial light water reactor fuel, so 5 weight percent and below. So what we're doing is we're recovering the uranium from our old EBR2 spent fuel and downblending it to 20%. So there are some sources there for the very near term that might support one of the microreactors, for example. But we've got to get a longer supply out. There's other opportunities to increase that in terms of recovery from other spent fuel sources, but long term we'll need an enrichment capability in this range.
All right, thank you. With your indulgence, Mr. McNerney, I'm going to ask Mr. Bowers one more technical question. You talk about systems that can shut themselves down. You evacuate the helium, you move off the coolant, and then you watch that system as it basically self-regulates. How in the world does it do that?
I did start out by saying I'm an engineer and not a physicist, but I can take a stab at it.
Okay.
Which is that there are within the uranium there are what's called resonances, and in these resonances at certain temperatures, rather than emitting neutrons, the uranium absorbs the neutron. So when you get to a particular temperature, you've got neutrons being absorbed instead of being expended, and that's basically what fuels the reaction. So as you
so that's not an implosion in of itself. What happens when they absorb those neutrons?
It returns to a more stable state. And the temperature goes down within the.
Do you have a temperature
core.
range for us? Do you know what that temperature range is?
It's between 1,000 and 1,100 degrees centigrade. Our reactor operates around 900 degrees C, and the outlet temperature on the helium is approximately 750 degrees C.
And time frame, is that 15 minutes, 15 hours? What's the time frame?
A cycle like that is predicted to be on the order of 25 to 35 hours. And so, each, a day or 2 days, you'd see it cycle up and cycle back down again. And it would continue in this kind of state for weeks, if necessary, until power was returned and you.
So if you restore, to arrest that cycle, for lack of a better term, or to restore it to its original.
To arrest the cycle, insert the control rods is the way that we would accomplish that. And we actually have two separate, in our particular design, two separate banks of control rods, one for operation and trimming performance and the other for shutdown.
Well, I want to ask you why that is, but I won't. So the gentleman from
Defense in
California.
depth.
The gentleman from California is recognized for his questions.
Well, I thank the chairman. And the chairman will be interested to learn perhaps that our colleague, Mr. Flores, and I introduced a bill called the Advanced High Assay Low Enriched Uranium Act, H.R. 6140, and the Energy and Commerce Committee was passed out of committee to enhance the cycle of producing high-end, this session. So that's it was going to be taken up on the floor this week, but for some reason it was pulled. And so I want to talk a little bit more about that, and thank you for carrying the water on that for me. Mr. Bowers, you said that by in your testimony, 2023, we'd have to have fuel ready for these reactors. What role do you see that private industry can play in establishing this supply chain?
supply chain of the high-assay LEU.
Yes, sir.
So recognize that where X-Energy intends to play is fuel fabrication, which means high-assay, low-enriched uranium comes into our facility in the form of an oxide, and then we use that to create kernels and particles, et cetera, that are then pressed into the form that we require. So it's like a raw material to us. And while if we were the people today that have the capability of generating low enriched uranium is Urenco in New Mexico, and they are the only producer today, or what's referred to as an enricher in the United States. In terms of where else I could, if the question is where could I, in terms of executing my business plan, get high-assay, low-enriched uranium?
Well, the question really is what role do you think that private industry can play in establishing that supply chain?
So I'll say this, there are companies in the United States, Centrus Energy is one that once upon a time had the significant enrichment capability. They still have the engineering and knowledge and understanding of what it takes to construct and operate an enrichment facility. And so private industry is prepared to do that. I think this again falls into that chicken or the egg element, which is what is the demand for low-enriched uranium between 5 and 20%, and if that demand is evident and orders are ready to be placed, a company will step forward and make that investment. But that's somehow we have to kickstart or jumpstart that industry.
And the federal government could be helpful in that.
Very helpful.
Thank you.
Thank you.
Mr. Bowers, I'm going to read this question. It's a little complicated, but regarding Nuclear Regulatory Commission licensing, the committee has repeatedly received testimony over the past several years that the current licensing framework is not suited to efficiently assess new generation of nuclear reactors. As you mentioned, the NRC and the DOE and the industry have taken some steps to modernize the licensing process and help alleviate some of the licensing costs. What specific regulatory changes would you like to see, and what steps can the NRC and other agencies make that would help this process become more efficient and quicker?
I think there's broad agreement on the changes that the NRC intends to put in place and recognition from industry of what those benefits would be. During my testimony, I mentioned the licensing modernization program. And the goal of that program is to establish a different way of looking at reactors and how do we license them. I like to use the example of a volume control. And so there's a requirement. I've got my car, right? I want to listen to the radio. I need a volume control. And so the requirement is I need to be able to control the volume. The way the NRC would look at that requirement is they would say the knob needs to be 1 inch in diameter, it needs to be painted black, and it needs to have white numbering on it. So very prescriptive in terms of how the requirement is met. And that works when every reactor is based upon the same technology, i.e. light water reactors. As we move forward and we have different technologies, molten salt, high temperature gas, fast reactors, that the NRC will need to regulate, they have to come up with a different paradigm as to how they will ensure safety of those systems. And so moving to something called risk-informed, performance-based assessment or analysis is the framework that they're looking to move to. And they are in the process of doing that. We have just started our pre-application engagement with the NRC, and so it's a little early on in the process. We've had a couple meetings with them. I'm very anxious to move forward, kick the tires with the NRC, and help them understand our technology and help them with their new framework.
Thank you. Mr. Chairman, I'll yield back to you.
Thank you, sir. The gentleman from California is recognized for questions.
Thank you. And Dr. Parsons, in your prepared testimony, you discussed creating a site where companies can deploy prototype reactors. And let me just note that we have, with your leadership, provided legislation, H.R. 431, which is Chairman Weber's bill, and that that's about to be signed into law. And we appreciate your leadership, Mr. Chairman, and your guidance on this. So that I think we've taken a step in the right direction. I would imagine that was part of your testimony today.
Indeed, we thank you for that.
Okay. Let's look at this. Again, I don't want to dwell on the fact that nuclear energy, I believe, is inherently dangerous, but we have to do certain things that are dangerous in order to succeed in achieving certain goals for civilization. And for the chairman was asking about how these things could be determined in case of an emergency, who would shut down that. And Mr. Chairman, I think HAL will make all those decisions for us. You remember HAL?
That was quite some odyssey, wasn't it?
HAL in the Space Odyssey 2001 was the computer got out of control, and we have already had some people suggest, Elon Musk for one of them, that if we go down too far down the road of everything robotic and letting them make decisions, perhaps wrong decisions will be made that are beyond our comprehension today. So as we move down that direction, obviously we have to have whatever system we put in place, we'll have to have a computer systems that will deal with the challenges, the new challenges that are brought up. Again, I would just suggest, and I am not, I don't have the engineering background, but from what I have heard today and from what I have gleaned from other hearings that we've had, is that light water reactors they are inherently more dangerous than what we are capable of building in terms of the non-light water reactors. Mr. Bowers, is that correct?
I'm going to phrase it a different way, which is that the light water reactors require active safety systems to maintain safety, and the advantage that and these are Generation 2 and Generation 3 reactors, the advantage that the Generation 4 reactors bring is that rather than having active safety systems that require human intervention, you have passive safety systems that do not require a human to ensure safety of the system. And I'll let Mr. McGinnis.
Well, do we not, inherently, do we not have more leftover waste from light water reactors than we would from the high-temperature gas-cooled reactor, for example?
I'm going to say that no free lunch. We create nuclear spent fuel the same way that a light water reactor does. Ours is packaged a little different. Rather than it being in control rods, we're in pebbles.
Well, the question isn't length of time. The question is amount of waste that we have to deal with. I am under the impression that light water reactors will produce more nuclear waste stuff that we deal with as compared to high-temperature gas-cooled reactors, for example. Is that correct?
I'm going to pass on that, if I may, and get back to you with an answer. I'm not a spent fuel expert, so forgive me.
But go right ahead.
Thank you very much. I would just love to have had some of our great innovators in NuScale and Holtec, and frankly, some of the other companies here that are working on game-changing both non-light water and light water reactors. Literally, the one that is progressing with a partnership with Idaho National Lab, UAMPS, a municipal utility in the Utah region with a number of states. This design is going through the NRC now. They're very conservative at the NRC, and it's a light water design. And so I would ask that if we could at least open the spectra a bit and give this design an opportunity to see whether NRC validates that this light water small modular reactor design can safely shut down on its own, and they've already validated that.
I'm more concerned about also the amount of nuclear waste.
Mm-hmm.
We have a storage facility that's being put at San Onofre, right in the middle of a huge residential. We're talking about millions of people live around San Onofre, including my family, I might add. And if there is a system that will produce less nuclear waste at the end of the process, we should go in that direction. And especially if we can build a system that eats some of the waste that's already been given to us and eats some of that as fuel. So I would hope that we get really serious in terms of not only just planning how to produce electricity, but how to deal with that waste as part of the equation. Thank you very much, Mr. Chairman.
Thank you, sir. I want to thank the witnesses for their valuable testimony and the members for their questions. The record will remain open for 2 weeks for additional comments and written questions from the members. The hearing is adjourned.